Welcome, ladies and gentlemen. I'm Rosemary Bartlett with the Pacific Northwest National Laboratory, and I'd like to welcome you to today's webcast, Advanced Energy Design Guide Recommendations Envelope Overview, the final webcast in the three-part series on the AEDGs, brought to you by the U.S. Department of Energy's Building Energy Codes program. For those of you wanting continuing education credit for the event today, a link will be provided at the end of the webcast. AIA members should write down the link and go to that link and provide us with their names and AIA membership numbers, and we will submit the information to AIA for their credit. In addition, anyone wanting a certificate of completion to self-report to a professional organization should write down the link to go and generate and print one. We're very happy to have as our speaker today, John Hogan with the Seattle Department of Planning and Development. Welcome, John. Please begin.
Thanks, Rose. Today we're talking about the Advanced Energy Design Guides, the AEDGs. This is the third in the series. We're going to focus on the building envelope. Previous sections talked about the lighting and the mechanical. I'm going to give you an overview of the guides in general, but since that was discussed in the previous sessions, I'm not going to spend too much time on that. My name is John Hogan. I work with the City of Seattle in our Department of Planning and Development. I've been working with the City of Seattle for over 25 years as a Senior Code Development Analyst. I'm a consultant to the Advanced Energy Design Guide Steering Committee, so I've followed the development of the past guides and work on future guides. I'm chair of ASHRAE's Project Committee for Standard 189, High Performance Green Buildings, and I'm a member of the Standard 90.1 Committee, former chair of the Envelope Subcommittee. Standard 90.1 is the energy standard for buildings except low-rise residential buildings. And this is the baseline for the AEDG, so it's an important document to be aware of. As of now, there are 4 different advanced energy design guides available. There's a retail guide, an office guide, a school guide, and a warehouse guide. On the slide here, you can see the logos of the participants who are working with ASHRAE on these documents. They've been developed in conjunction with the AIA, the American Institute of Architects, with the U.S. Department of Energy, ASHRAE, the U.S. Green Building Council, USGBC, and IESNA, the Illuminating Engineering Society of North America. These are the lighting designers, and they are also co-sponsors of Standard 90.1 for many years. The guides are available now. They're on ASHRAE's website. You can download electronic versions for free, www.ashrae.org/AEDG. Here's what the homepage looks like. Move along here to give you a little overview of the AEDGs. First, it's a series of publications designed to provide recommendations for achieving 30% energy savings over the minimum code requirements of Standard 90.1-1999. So ASHRAE has published updates since then, but that's the baseline. And I want you to also be aware that these AEDGs cover key areas, key measures for energy efficiency, but they do not cover every single item in Standard 90.1. So where items are not addressed, the underlying assumption is that these components comply with Standard 90.1. So again, another reason why it's important to be aware of that. These documents are also intended for contractors and designers who are creating small buildings, and primarily it provides a simple approach to achieve these energy savings without having to resort to detailed calculations. Obviously, if you've got a 40-story office high-rise, you're doing detailed evaluation, you can do the hourly simulations, optimize your design. If you've got a smaller building, it isn't always feasible to do that sort of analysis. Now, the guides published to date, I mentioned the 30% energy savings. That's the goal for the first series of guides. The 4 that are available, small offices cover buildings up to 20,000 square feet. The small retail also covers buildings up to 20,000 square feet. Schools has a little different focus. It covers elementary schools all the way through high schools, so it covers some larger buildings there. The warehouse and self-storage guide covers buildings up to 50,000 square feet. Now, there are more guides being developed in this 30% savings group. The next one coming up is highway lodging. That's not too far from publication. There will be some more guides in the 30% series, and then ASHRAE will be stepping up to do a 50% series, and that will probably start in the next 1 or 2 years. Now, if we look at the guides, they address different building types, and they do have some different recommendations, different energy efficiency strategies, but they all have a similar organization. So here's an outline of the guides. So Chapter 1 is an introduction. Chapter 2 talks about the design process and see how to use integrated design and how that's important for achieving the energy savings. Chapter 3 contains specific recommendations by climate zone. Chapter 4 gives some examples of technologies, but also case studies for entire buildings. Chapter 5 is broken down into a lot of small sections with tips on how to implement the recommendation. And then there's Appendix A, which has envelope overall assembly U factors, if you'd like to use that as a way to show equivalent energy performance. And what I'm going to do is step through these chapters one by one. I'll skip over the introduction and just move on to Chapter 2. So Chapter 2 for the integrated design process, this calls for design choices to be made in this order as we go through it. And when I'm talking about all this material in this session here, I'll be taking excerpts from each of the various AEDGs. So they vary a little bit from one document to another, but I'll be taking pieces out of that. The 5 steps listed to looking at the site first to optimize on-site resources, such as daylighting. And the second step is to reduce any loads you might have. And then next is to, once you have that load, to size your systems properly that are serving those reduced loads. Fourth step is using efficient equipment and systems to serve the loads. And finally is doing some refinement of the systems integration here. So sort of loop back around and make sure you hold everything together here and optimize. In terms of the building envelope, the first 2 categories are the ones that are most important. Later ones focus a little more on HVAC and mechanical systems. So I'm going to focus on the first 2 categories. Now, when we look at the first set of design choices, the one to assess the site, 4 key factors here. One, evaluating where the project is located in terms of the center of the community. This is a larger, big picture issue, so it's focused more on transportation energy. Obviously, if you locate an office building, for example, 10 miles out of town, then workers must use more energy getting themselves back and forth to work. So this isn't so much a building energy consumption issue, but it's an overall energy consumption issue. If you look at the second point, evaluating access to public transportation. So even if you've located this office building within town, if you've got it nearby to not only 1, but maybe 2 or more bus lines or train lines, this means lower transportation energy for the workers to get back and forth. Next one is identifying on-site energy opportunities, and we'll talk about that more in a minute, and also working with the best orientation. In terms of on-site energy opportunities, you want to start with the integrated design. So you want to think about the site assessment. There are good sites and there are bad sites, and so you want to, if you have the ability to influence that selection, think about one that's going to be beneficial to utilizing natural resources so it can minimize your energy loads. Obviously, the resources are there, and so they're free. Make the best use of them. And let me give you some examples of different ones here. So here, I've got an example of daylighting. So you want to take an advantage of daylighting. So if you've got a portion of the site that's, you know, shaded by buildings on several sides, and another portion that's more wide open. If you move the structure towards that more wide open portion, you have more daylighting availability. You can use that to cover most of your lighting needs in many locations during the daytime. This is an example of a retail store in Montana and what they've done to take advantage of the daylighting. Obviously, another opportunity is to use passive solar heating to reduce the heating loads. Here's an example of an office building. Obviously, you've got the windows that are facing towards the south here, and so you're getting good passive solar gain. Third site opportunity is working with overhangs to reduce the cooling loads. And this is an example of a retail learning center in California where they use the overhangs to provide some shading. And another opportunity, of course, is having photovoltaic panels to reduce the amount of electricity that needs to be produced by fossil fuels. This one's actually in Seattle, and yes, it can work in our cloudy climate. The key thing is, as you think of the big picture, if buildings are going to use energy, and they are, buildings are really going to need to start producing their own energy, not just drawing on energy from off-site resources. So this is definitely a thing to take a look at, the PV, and obviously you can also use solar panels for water heating and for pool heating too. Now the second set of design choices refer to reducing loads on the energy-using systems. And several different opportunities, categories presented here. First of all, you want to reduce the internal loads that come from office equipment or appliances or even the overhead lighting. So if you use more efficient equipment, that means it's going to put less heat into the space, and that means you're not going to need to do so much cooling. So you'll save on space cooling as well as the energy from those appliances and equipment. Another key factor, and we'll talk quite a bit about this later, many options, is to reduce the heat loss or heat gain through the building envelope. But before we get to that, also think about reducing the thermal loads. So again, as mentioned a minute ago, if you work with passive solar design or with thermal storage, you can take advantage of opportunities there. So even if you have some loads, you're offsetting those. And lastly, take a look at how your building fits within the specific design conditions on the site. Obviously, if you've got operable windows and you can set something up where you get cross ventilation, you get some natural ventilation, that's a good way to take advantage of the site and reduce the energy consumption. And again, it may influence where in the building you place the site, where in the building you place the openings in terms of what adjacent buildings are nearby. Now let's talk about the reducing the heat loss and heat gain through the building envelope. And so this is going to be one of the key topics that we'll go through today. So first of all, one thing you can do is control the solar gain to reduce the cooling load. And primarily you're doing this through windows. So you want to take advantage of the building form and orientation. Preferably, you'd have the long axis going east-west. And that would mean that you would have a minimum number of windows, surface area and windows on the east side and on the west side. When you do that, it means that you have more windows on the north and the south side, and you want to maximize those relative to what's on the east and the west. But I want to be careful. We want to make sure you understand that this is within limits, that simply throwing glass at a building does not make it sustainable. A lot of buildings out there that have large south-facing glass areas that have high energy consumption and are not very comfortable for the occupants. You know, if you've ever been in, for example, a passive solar greenhouse or, you know, a sun space that's on the south side of the building, and you go in and people say, oh, this works so great, you know, during the winter time and the spring and fall, you know, it's hot here all the time. That's the exact example of something that is not well designed. It means it's got too much solar gain. It doesn't have storage to moderate the effect. And so too many windows can cause problems, can cause discomfort, and that'll mean callbacks for you if you're the contractor or designer on this. In terms of the glazing, if you work with the low solar heat gain coefficient, obviously, again, that minimizes the cooling load, and that's the aspect that we're talking about at this point. Another way to minimize the cooling load is to do some external shading, such as with overhangs, to reduce the solar gain. A couple benefits from this. One is if you block the sun from even hitting the glass, that means the glass is not going to warm up, and so there won't be such a hot surface, warm surface in the space. And the other benefit is it reduces glare so that people who are working near the window don't have as much glare. Other aspects, a way to control the solar gain to reduce the cooling load is to use vegetation. On the east and the west, you want the vegetation because you've got the low sun angles, and having plantings there will help that. On the south side, you want to structure the plantings carefully so that they will shield during the peak cooling days of the year, such as during the summer, but will not provide so much shading during the winter time. And it's not always understood by everybody, but even deciduous trees provide a fair amount of shading with their branches alone. So you could have a deciduous tree that loses all its leaves, and some of them have so many branches that they provide a blockage of 25 to 50% of the sunlight. So if you are doing things on the south side of the building, be careful and thoughtful about that. Other ways that people do shading with low-rise buildings is they do vines or other vegetations on trellises, and things like that will not have what we call the tree branches that are blocking everything throughout the year. You also want to think about reducing solar gain through opaque surfaces, and in this case, obviously, increasing the insulation will reduce any solar gain. Solar gain, much of the time, is during the summer, and that means the roof. And so if you can increase the reflectance and emittance, then you're going to do a good job of just bouncing the heat off the roof before it even starts to go through the building. And also here, the opportunity to shade these surfaces with deciduous or coniferous trees, or depending on the orientation. Other steps here, if you want to reduce the conductive heat gain and heat loss. So this is once you have the shell of the building, this is how much heat's actually moving through it. And with this, the key steps are to increase the insulation everywhere you've got it. So roofs, walls, floors, the 5-on-grade floors, better doors, and to also decrease the window U factor. So that's the measurement of how much heat will flow through the window itself. Another key step is to reduce air infiltration. So people do very good jobs with the insulation and with the windows, but when you get to a building that's that well insulated, then the next step, important factors become air leakage. And so one of the goals would be to install a continuous air barrier so that there's no leakage. And people sometimes think that they just need to seal around doors and windows, and those are important things to do. But you need to be caulking sill plates. You've got loss coming through electrical outlets in the walls. People have situations where they've measured a lot of air leakage going through interior partition walls up into attic spaces in the roof. So you really want this continuous air barrier to go around all the wall surfaces and whatever ceiling or roof surfaces are enclosing the conditioned space. A good way to check for this and check your performance is to have a blower door test done, where they actually bring a device up, which would be mounted, for example, in one of the doors of the building. They turn on a high-power fan, and then you can see how much pressure the building can hold, and that will tell you about air leakage. And a way to evaluate that and improve it is to use a smoke stick, and that will quickly show you where the air is going in or out of the building, so you know where you need some additional caulking. The last step here is to reduce the heat gain or heat loss from ventilation exhaust air. In colder climates, if you're just taking the air in and then pumping it right out, you're losing a lot of the heat capacity of that air. So if you can do a heat recovery system, so you take that exhaust air, you recover some heat from that, and you connect it with the ductwork for the incoming air, then you can preheat that incoming air, and then you don't have to use as much energy for that. Now let's go on to Chapter 3, and this has the recommendations by climate zone. And I'm going to show you examples for a variety of different climates from hot to cold, but before we start into that, I wanted to give you a little background information. So the way the AEDGs were developed, they started with some base documents, for example, ASHRAE Standard 90.1, and there is additional information in those documents. So, for example, the AEDGs do not have all the definitions, and the AEDGs do not have requirements for every single component in the building, and those are contained in Standard 90.1, so that's a good reason to take a look at that. And also there's the user's manual that accompanies Standard 90.1, and one of the benefits of this, it explains the criteria a little more in Standard 90.1, but it also has different examples. So you're not just reading the dry language, you get a much better sense of what the intent is here and how to apply things. So those are both good documents to have when you're working with the AEDGs. And as we go through the AEDGs, again, there will not be criteria listed for every single component in the building envelope. And where there are not recommendations listed, the energy analysis has presumed that all the other components are built to the standards 90.1 and 62.1. So again, if you're working in some aspects of the building, you don't see it covered in the AEDGs, go back to these other documents for reference there. Now let's start to go through the particular requirements here. Here's the climate zone map for the United States. You can see climate zone 1 is down in the southeast. It's Miami area, also includes Honolulu, Puerto Rico. You can see climate zone 2 is primarily in the southeast, Gulf Coast. Climate zone 3 through much of the south and also much of California, coastal California. Climate zone 4, middle of the country through Washington, D.C. and also the northwest coast. Climate zone 5 starts to move up into areas, Boston, New York, some places in the mountainous areas of the west. Climate zone 6 is northern New England and much of the northern plains. Climate zone 7 is the very northern portions of the Midwest, the northern tip of Maine, some places in the high Rockies. Climate zone 7 also includes the southern half of Alaska. And then climate zone 8 is the northern half of Alaska. So take a look at this, get a sense of where your particular city falls. So as we go through some of these tables, you'll know which table applies to you. I'm going to show you examples for 4 different climate zones. So these are going to be climate zone 1, 3, 5, and 7. If you're in one of the even-numbered climate zones, you can look at the odd-numbered ones above and below that and get a sense of roughly where the criteria would fall. Well, let's start with climate zone 1. So Miami, Honolulu, San Juan, Puerto Rico. I'm going to talk first about the insulation requirements. So these are insulation requirements for roofs, walls, and floors. This is the minimum insulation R value. So, for example, you see if the roof has insulation entirely above deck, which is quite common for most commercial buildings with flat roofs, you need R25 insulation, and it needs to be continuous insulation. This is usually rigid insulation, often about R5 per inch, so this would be about 5 inches of rigid insulation. Also be aware, if you're tapering the insulation, this is the minimum R value, the R25. For attic insulation, it's R30. This is typically blown-in insulation, fiberglass. Oh, and by the way, as I talk about specific insulation types, I will talk about what are the more common types that are used, but there's not a limitation to that. So when it says R25 continuous, you can use any type of insulation that would get you R25 continuous. The attic insulation, it can be blown in fiberglass, but cellulose, any other type of material that can be used there also. R19 for metal buildings. This is typically going to be insulation that's installed between the roof structure and the girts. And so it's laid over the girt and compressed between the roof and the structure itself. And here you see an SRI, the Solar Reflectance Index of 0.78. I'll talk some more about that in a minute. In the wall category, there's 5 different types. There's a mass wall, so this is typically going to be masonry block wall. It has heat capacity greater than 7, so this will not include categories where people are doing face bricks, say on a steel stud wall or a wood frame wall. This is really more a concrete block wall or concrete walls to meet that heat capacity greater than 7. And this calls for R5.7 continuous insulation. So this is rigid insulation. When used in the wall, rigid insulation varies between R3.8 to R7 or 8 per inch. So this could be, for example, 1.5 inches of rigid insulation in a mass wall. So, and this calls for it to be continuous. That means it's uninterrupted by framing. So that means you've got it attached with some very small clips or something so that you don't have metal framing or even wood studs that are short-circuiting the insulation R value. Steel framing, steel studs, R13. That's the medium density batt that would fit in a 2x4 stud. Wood framing, same R13. Metal building, similar criteria. Below grade walls, you see the reference here to comply with standard 90.1, so there's not a separate criteria here for below grade walls. Last category, floors, mass floors. So you might not see this so much in smaller buildings, but if you had a concrete floor over a parking garage, for example, or if you've got some sort of bay windows or building overhangs that have to be made out of concrete or something, so it's more a building overhang, probably not so much a bay window unless it's a floor-to-ceiling bay window. Calls for R4.2 continuous insulation. Steel framing and wood framing are 19 between the joists there. So having given you a quick overview of these criteria for Climate Zone 1, let's talk in a little more detail about some of these categories. So the R value, this is the R value for the insulation alone. So it can be insulation that's either continuous or in framing cavities, but it does not include air films, does not include building materials. So this is a very simple, very easy way to figure out what the criteria are. So it doesn't matter whether you're doing gypsum board or tongue groove sheathing or T111, whatever you're using for the exterior surfaces or interior surfaces of the wall or the roof. It's just only the R value insulation alone. Where it does say CI, though, it must be continuous insulation. So it means no framing interrupting the insulation. And this is simple. It's easy to understand. Of course, there are a lot of creative people out there, and there are ways to do other types of wall construction, roof construction, floor construction. So if you have some unusual construction, you can look at Appendix A, and that has the U factors for these assemblies. And so you can show compliance on an overall U factor basis. And then it also has the C factors, which are for low-grade walls that don't include the hair films, and S factors, which are for the perimeter of slab-on-grade floors. And so those are per lineal foot of perimeter as opposed to per square foot of wall or roof. Now the Solar Reflectance Index, essentially their criteria for 0.78 means that you need some sort of cool roof. And these values are ones that come from a third party, such as a lab accredited by the Cool Roof Rating Council. So you don't need to worry about the pitches you're getting from manufacturers and whether you understand all the technical details. Just indicate to whoever the rep is, that you want something that's been rated by the Cool Roof Rating Council, and that way you know it's third party and it has credibility. When you look at these different options here, you can see there's some single-ply roof options. There are some liquid-applied coatings that can be installed, and there are metal panels. When you look at the single-ply and the coatings, you see that most of these are white coatings. And you see some of them have pretty high SRI values, you know, up to 107, and the criteria is 0.78, so that's, you know, 30% beyond what their requirements are. When you look at metal panels, the example given here is with a white finish. But people are getting very good with some of these different coatings, and so you'll be able to find that you can get different colors. You're not limited to white to achieve these higher reflectance and emitting values to meet the specified SRI. So take a look at that, and the primary benefit here, this is the Miami climate zone. We've got sun that is way overhead during the summertime, and so we're trying to minimize the heat that's going through the roof and is adding to the cooling load. Now that you understand the criteria for the these tables, so let's go through a few other climate zones. Let's go to climate zone 3. This includes places like Memphis, Atlanta in the southeast, but also El Paso and Las Vegas in the west. For the roof with the insulation above deck, here the criteria is R25 continuous insulation, so it's the same as it was for the very hottest roofs in Miami. For attics and other roofs, the insulation level has gone up a little bit. Now it's R38 instead of R30. For metal building roofs, you see a double layer here. So it's the R13 layer, which is draped over the girts, but it's also another R13 layer, which is placed between the girts. And also, again, the 0.78 SRI. So still in these climates, and you can imagine that they had hot roofs in El Paso and Atlanta and Las Vegas, so here the SRI is important to minimize the gain during the summertime to reduce cooling loads. Mass walls, up a notch here to our 7.8 continuous insulation. Steel frame walls, now you see R13 cavity insulation plus R3.8 continuous insulation. Challenge with steel framing is there's a lot of short-circuiting through those metal studs. It's that R13 that you're putting in the cavity there, you're only getting approximately half of the insulation R value for that. Those skinny metal studs, they may be thin, but they have such a high heat conductivity that the heat just flows right around the insulation. So it's much better to be doing continuous insulation over the studs. You know, if you need the studs there to attach gypsum board or something else, go with some minimal thickness on the studs, and then as much continuous insulation as you can to break those thermal bridges. Wood frame walls still at R13. Below grade walls, still no requirements. The mass floors, again over parking garages, slightly higher, R8.3 continuous insulation. Steel frame walls, floors, R19. Wood frame floors now slightly deeper here, R30. And let's look at a few other categories. Going to climate zone 5. Now we're further north. So Chicago, Boise, Boston, places like Vancouver, British Columbia, just across the border in the northwest. Same roof insulation, R25. And so what is happening here, it's got the same R value, but the R value is serving different purposes. So the R value in Miami was working to prevent the heat from coming into the building, so to minimize the cooling load during the summertime. Conversely, as we start to get into these colder climates, the sun doesn't get quite as high in the summer, but it gets much colder in the winter. So it's the same R value, doesn't have as much of a benefit during the summertime, but it has more of a benefit in the wintertime. And you put those two together and you end up with a similar R value. Attic insulation, R13, Metal building R13 plus R19. So the compressed insulation R13, the R19 between the girths. Now you're seeing we're getting to colder climates. You do want the thicker insulation values. For SRI, the solar reflectance index, it's saying comply with standard 90.1, so there is not a specific requirement here. Because they're northern climate, there's not such a cooling load, there's not a special criteria. Mass walls, higher insulation are 11.4 continuous insulation. Now for all the other wall types, you see cavity insulation plus continuous insulation. So the steel framed wall in Chicago, R13 cavity insulation plus R7.5 continuous insulation. So this could be anywhere from 1 to 2 inches of continuous insulation depending on what the type of rigid insulation is that you're using. Wood-framed walls are R13 cavity insulation plus R3.8 continuous insulation. And metal building walls are R19 plus R5.6. So more insulation here for those walls. Below-grade walls, now with some insulation requirements, are R7.5 continuous insulation. Typically, the insulation material used for below-grade walls and for slab-on-grade floors is about R5 per inch. So this is 1.5 inches of rigid insulation. Continuous insulation can be easily installed on the outside of the building. Have the earth backed up against that. That gives you lots of flexibility with how you finish the inside of the walls of below grade. Make sure that when you're carrying that up, that you carry that up to cover any of the basement walls that go above grade. So maybe you've got 6 inches or a foot above grade. Carry the insulation above that and make sure you've got some protective surface over that. Because the ultraviolet rays of the sun or landscapers out there are going to start either degrading it or chipping away at it. So make sure it's got some rigid covering over it to protect it from the weather and from landscapers and also irrigation systems too. For the floors, mass floors, another step up here to R10.4 continuous insulation. Steel framed and wood framed floors are 30 continuous insulation. Now let's look at the this cavity insulation and the continuous insulation. I think you have a pretty good sense of how that works, but you want the cavity insulation to be minimized. You want as much continuous insulation as you can get so that you offset the thermal bridging. And here's a graphic that's in one of the guides. This one's in the Advanced Energy Design Guide for Warehouses. This is the envelope tip number 8. So this is in the chapter 5 of the guide. So the material that I've been discussing with you, when you look at these tables in the Advanced Energy Design Guide, they give the tips off to the right-hand side. You can just flip back further to the guide and it'll explain more what that means and what design options you have to work with that. And let me talk lastly about coldest climates, climate zone 7. This is Duluth, the very northern portion of the lower 48, as well as Caribou, Maine, and then the southern half of Alaska, such as Anchorage. Here the roof insulation, R25 continuous, but for attics now it's up to R60 insulation. Metal buildings R13 plus R19. No requirements for solar reflectance index because it's a colder climate. For the walls, again, the insulation levels keep stepping up. Mass walls now up to R15.2 continuous. Steel framed and wood stud walls R13 plus R7.5 continuous insulation. And metal building walls and below grade walls similar to before. For floors, mass floors up another increment to R12.5 continuous insulation. And steel frame floors up to R38 continuous insulation. In addition to those general requirements, which apply across much of the guides with some slight variations in insulation R value, some of the guides have specific requirements for particular building types. And for example, the warehouse guide has a requirement for loading dock weather seals, and this applies for all climate zones. And it sets maximum infiltration levels both with doors open and how you address infiltration when the door is closed. So when it's closed, you want the maximum leakage to be the 0.28 cubic feet per minute per square foot of door area. When it's open and you've got a door in place, a truck in place, you want to make sure that there's a seal around the edge of that. So some sort of door leveler or some inflatable or foam type of seal so that you're minimizing infiltration in those gaps. And again, here if you go to the AEDG for warehouses and look at envelope tip number 13, it provides more detail on that. Now let's shift over to fenestration. And in terms of the fenestration, I'll do a similar thing, go through 4 different climate zones here. We'll talk about what the category of requirements are first, and then a little more detail about what each of them mean. So climate zone 1, again, Miami and the tropics. So the total fenestration area to gross wall area ratio, 35% maximum. So this is, fenestration is an architectural term. It means all the openings in the building. So it's windows, doors, it's skylights, it includes all those different terms. But essentially what this means for the wall is it's the area of window divided by the gross wall area. And it's saying 35% maximum. And this is an issue to help minimize solar gains during the day, which affect cooling, but it also minimizes heat loss at night, which affects the heating load. The thermal transmittance, U factor for all the windows is 0.56 maximum. The solar heat gain coefficient for all orientations is 0.25 maximum. And for exterior sun control for the south, east, and the west, but not the north, is to have a projection factor which is 0.5 or greater. Now let's talk a little bit more about what these particular items mean. So the fenestration area, when you're calculating that, it's the entire rough opening area. So it includes the glazing, but also the sash and the frame. And it's not the glass area. So again, it's the rough opening area. It's pretty easy to calculate, but it is based on that rough opening area. The U factor, the thermal transmittance, this goes back to standard 90.1. It refers to having these determined in accordance with NFRC 100. NFRC is the National Fenestration Rating Council, and this group was established by the Energy Policy Act in 1992 as the preferred entity for developing the window energy rating system. The standard 100 addresses U factor. All these ratings are for the overall product, including the glass and the sash and the frame. So it's not just the center of glass. You will see people talking about the center of glass and the center of glass performance. And part of the reason is the center of glass can have quite a bit better performance than the whole product. If you have a product with a metal frame, that you could have a center of glass U factor of 0.3, but with the metal frame, the performance could be 0.60 overall. Because there's so much heat loss through that frame. There also are higher U factors for products that are at a slope, like if you have any atrium or slope skylights. For solar heat gain coefficient, also to be determined in accordance with NFRC 200, and I've given you the section references in ASHRAE standard 90.1, is for example 5.8.2.5, so you can refer back to that document if you want more details. But once you have those two ratings, an easy way for you to verify that as a contractor and also as a designer if you're doing site inspections is to look for a label. Because you've got a manufactured product where the entire product is being constructed in a plant and then shipped to your site, construction site, there'll be a 4-inch by 4-inch label that's put on at the factory. Conversely, if you've got a site-built product, so if you've got a glazed wall system or a curtain wall, what you get is an 8.5 by 11-inch label certificate that has this 4x4 label in the corner. Now let me show you the 4x4 label, NFRC label. So the upper left has the NFRC logo, the upper right has a description of the product. This particular one, for example, Says it's vinyl-clad wood frame, it's got double glazing, it's got argon gas between the two layers of glass, it's got a low emissivity coating, which makes 2 panes of glass perform as 3 because it's got better solar control, for example. And the product type is a vertical slider. And then the U factor for this product is 0.35, which happens to be the criteria currently for Energy Star in the northern 4 climate zones of the country. Solar heat gain coefficient of 0.32, visible transmittance of 0.51, and air leakage of 0.2. If you're trying to refine your design, and if you're thinking about daylighting, you want the visible transmittance to always be higher than the solar heat gain coefficient. If you look at bronze glass or some of the mirror-coated glasses, you find the visible transmittance is low and you have more of a gloomy space. But it's very easy to find visible transmittance that is 1 1/4, 1.5 times the solar heat gain coefficient. And there are products out there that are even 2 or 2.5 times. So you might find a solar heat gain coefficient of 0.3, but a visible transmittance of 0.6. So you can get a lot of light with very little heat. So that's an important factor when you think about daylighting. But moving on to the NFRC label certificate, again, this is 8.5 by 11 with the 4 by 4 in the corner. Now that table that we looked at also talks about the projection factor. So the projection factor is another fancy word for overhang, but there's a variety of different ways to do this. And so sometimes when you think about overhang, you just think, oh, this is going to be concrete slab projecting out or something like that. To calculate the projection factor, you take the width, how much the overhang projects out, and then you divide that by the height of the overhang from the bottom of the sill of the window up to the bottom of the overhang. But as you see in these 2 examples, it doesn't have to be a solid overhang. You know, here, for example, there's a slatted overhang that you could use. Another option, you know, the overhang doesn't necessarily have to be right at the top of the window. So you can see in the example on the right there, that graphic says the overhang is slightly higher, so it's not mounted right at the top of the window. But again, the graphic indicates what you take for the projection and what you take for the height when you're doing that calculation. Projection factor of 0.5 means that if the height measured here is, say, 4 feet, that the projection would need to be 2 feet. Now, we're also talking about the projection for each portion of the window. So in lieu of having 2-foot projections for the entire 4-foot, you could have a 1-foot projection every 2 feet or something which achieves a similar result. Let's go on and look at some of the other climates here. So moving into a little cooler climate, climate zone 3 in the southeast and southern portions of the west. Same fenestration area here, 35% of the wall maximum. Thermal transmittance 0.45, so now we've got a lower U factor here with 0.56 and the other one now it's 0.45. And I'll show you a table later on that's in the Advanced Energy Design Guide to give you a sense of what those correspond with. And solar heat gain coefficient, again, 0.25. So it's a lower number here. Essentially what this means is that if all the sun striking the window, only 25%, only a quarter of that gets through the window. The rest of that gets bounced back out or absorbed by the glass. And this also calls for the projection factor of 0.5 or greater. When we go to climate zone 5, a little more northern tier of the continental 48, same fenestration area, 35% maximum. U factor is now even lower here, 0.42. But the solar heat gain coefficient is higher now. It's up to 0.40. So as you start to get to the northern climates, heating starts to become a little more of an issue. Cooling is not as much of an issue, and so the requirements are relaxed a little bit here for that. And lastly, for climate zone 7, same maximum window area, 35% of the wall. Thermal transmittance now quite a bit lower here, 0.33 U factor. So the heat gain coefficient now is higher. Now it's up to 0.45. Same projection factor, 0.50. But as you're thinking about commercial buildings, sometimes people only envision what happens during the day, and they think, oh, there's lots of cooling going on because I've got the people there, the lights and equipment, and so cooling is really the concern. So do I really need so much insulation? And the fact is these commercial buildings tend to have a bimodal operation. So during the daytime, when they're occupied, let me just say from 8 to 5, the sun's out, people are there, lights and equipment are on, and so it's cooling, that's true. But the primary time when the heating takes place is morning warm-up. So it's 5 to 7 a.m. Sun's not up yet because it's more, I'm talking about the winter time here. There are no people in the building. If there are any lights, it's sort of minimal lighting for exit lighting. Very little equipment's turned on. So, but you know, of course, when everybody gets to the building at 8 o'clock, they want it to be 70 degrees. They want it to be warm. And so that's when the morning warm-up takes place. And so not an issue of figuring out what's more important during the day or what's more important at night. There are two different phases of building operation you need to think about. You need to have good insulation and good window performance for morning warm-up when there's nobody there and it's cold and there's no sun. But you also want good performance during the day when you have all the people and the solar. Now let's go on, and here's a table which shows how you might achieve some of these criteria. So for the package for the hottest climates, which had a 0.56 U factor and 0.25 solar heat gain coefficient, that's typically going to be double glazing in clear glass, meaning it doesn't have a low emissivity coating, the metal frame, but it's got a high performance tint on it, and so there's some reflectance to it to bounce the solar gain out. But there's nothing special about the other coatings on the glass or about the frame. To get to the 0.45 U factor, it's double glazing, it's got the same type of glass in it, but now you've got a metal frame with a thermal break. So if you think about a metal frame, there are several ways that people do the thermal breaks. They can provide 4-inch bridge thermal break where they actually have a piece of rigid material that's more insulating that actually holds the inner portion and the outer portion of the metal frame together. And that's the older technology that's been used for a long period of time. Nowadays, people are starting to use some thermally improved frames where they're actually trying to bury a lot of the frame, the metal, inside the building, and then have the glass on the outside of that, and then there's just a thin little cap that is screwed through and attached to the frame. And this way, the thermal bridging gets reduced significantly because it's primarily the screws that are going through from inside to outside, and you don't have thick pieces of metal going all the way through. The next step down here, this is more for climate zone 5, was a 0.42 U factor, 0.4 solar heat gain coefficient. In these situations, it's double glazing, and one pane has clear glass, and the metal frame has a thermal break. But the other pane has a very good low emissivity coating with an emissivity of 0.05 or lower. So there are several types of low emissivity coatings. There are pyrolytic, or also called hard coats, that are actually baked onto the glass when the glass is made. And then there are the soft coats, the sputter coats that are put on by a vacuum deposition process later on. The sputter coats don't hold up as well to the outside environment, so they're always installed on the inside of glass. The pyrolytic, the hard coats, they're the type of things that people can use in storm windows. And we've got projects in Seattle where people are putting 2 lowy coatings on this double glazing. So they've got one which is the sputter coat which faces the inside and of the air gap, and then they've got the hard coat, the pyrolytic, which is actually on the inside surface facing where the occupants are, so that you can actually wash that, and people can touch that window and it doesn't degrade. The fourth window option here, the 0.33 U factor with a 0.45 solar heat gain coefficient. This is double glazing, clear glass one side, low E coating, very good low E, but this has a very good frame. So this has a vinyl or an insulated frame, or this includes something like wood frames. So again, if you're using or constructing smaller buildings, could have wood frames, could have vinyl frames. Another option newer on the market is fiberglass frames, and those actually tend to perform the best of all. And there are different composite frames, mixtures of both of those. With vinyl frames, if you get the vinyl frame insulated with some material such as fiberglass, or if you get the fiberglass frame with insulation inside the frame, not just an empty cavity, those will perform even better. So those are good steps that you can take. Now, a few other criteria for window orientation. There's a requirement for all climate zones that the area of the glazing on the east and the west times their solar heat gain coefficient must have less solar gain than that on the north and the south. And so if you've got a square building, this means you put a few more windows on the south and north and on the east and the west. But this also addresses orientation. So this is encouraging you to design the building so that most of the windows are on the north and south, and there's not so much window or window area on the east and west. There's also a criterion here for daylighting. And this starts to get more ambitious here, but I wanted to show you some of this and point out some of the tips and recommendations. So this is from the AEDG for schools and talks about classroom daylighting. And it talks about the area that you need for daylighting relative to the floor area. So if you're daylighting these classrooms from above, you need roof monitors, which are only 8 to 11% of the floor area. If they're south-facing, or they could be slightly larger, 12 to 15% of the north-facing. If you're doing this through side lighting, through windows, the south-facing windows, 8 to 11% of the floor area, north-facing, 15 to 20%. So you see this is a relatively small percentage. This is not floor-to-ceiling windows. And if you're combining those two, then you can see the percentages are smaller. Now the ways to do some of this daylighting, and this is again for classrooms. If you take a look at this picture here, if you do something where you float the ceilings, it will bring the light further back into the space. The left side of this graphic shows the south side, and it's a top floor, second floor on the south side. You see the sun coming down, hitting this overhang light shelf, and then bouncing up inside the building through some glass and then going further into the space. And on the first floor, you see the other part of that graphic. To the extent that you've got that overhang, it's going to block the sun from coming through the lower portion of the window there, so there's less glare on any students that are at desk near the window. When you look at the north side of this, on the right side of the building, you don't need any of those light shelves, you don't need the overhangs, because there's no sun to block on that side. So as you're doing your building, be thoughtful about how you treat different facades. So here's an example of the north-facing classroom with the sloped ceilings. And there's a light fixture running through the middle of this, but if you look beyond the light fixture, you can see just a straight wall there. So there's no light shelves or anything bouncing that light further back into the building. Now you want to, when you do this, figure out what the cutoff angles are and get something that will work for your climate. Obviously it's going to be different south versus north. In the south, the sun angles tend to be higher, and so the overhangs don't need to be so long. In the north, the sun tends to be lower, and so the overhangs a little longer. But here are two options. On the left, you see an option for doing one continuous element, which has a little overhang on the outside, but then a light shelf on the inside to provide the shading and bounce it up. But you could do a tier of these, you could have 3 different light shelves on the inside to provide the cutoff angle that you need. For the light shelf detail, now here's another little different one. So here, there's no real light shelf on the inside of the building. This is all handled by sort of combination light shelf overhang on the outside of the building. And then you see the slatted louvers above there to prevent the sun from coming directly into the space. This one happens to have a couple of dimensions here. You can take a look at this. People who are fine-tuning the daylighting design, they will tend to put glass on the lower portion of the building where people are sitting, which has a little better solar control, a little better solar heat gain coefficient. And then the upper portion of the glass could be clearer because that's where you want the light to bounce through the glass, up against the ceiling, and further into space. And so the dimensions they're giving here are something having the lower portion of the glass about 30 inches tall and the upper portion about 24 inches tall. The top lighting alternative is can be trickier because you've got the sun coming in a variety of angles, and if you're only having one orientation, so you've got a south-facing roof monitor, you're going to have to stagger any louvers on the inside of the building to make sure there's no direct sun that's coming down on students' desks, because the glare would be not helpful in terms of reading or different things they need to pay attention to. And here's an example of a gym. And this is done with top lighting. So we're not only talking about classrooms, but there are a variety of different spaces that are within a school building. So that's a quick overview of the recommendations in Chapter 3. There are a couple of other chapters, as I mentioned, the Chapter 4 and Chapter 5. Within Chapter 4, that has the technology examples and the case studies. Almost all the examples that I've shown are in the AEDGs, but these are only a small percentage of all the ones in the AEDGs, so look there for more. Similarly with Chapter 5, that has the how-tos, the tips for implementing the recommendations. I've shown you a few of those, but again, it's but a small sample of the ones available in Chapter 5 of the various AEDGs. So this is the website. The guides are available. Go to the website for the free download of the electronic version. And this also can provide you information about the status of other guides that are under development. These are good resources. Take advantage of them. And that ends our presentation for today.
Yeah, thank you very much for such an informative webcast, John. And thanks to all of you. The U.S. Department of Energy appreciates your attendance today.